Hello, friends. So today we are going to talk about sheet pile. Is another important chapter for many competitive examinations, and from your academic point of view. As you know, that sheet pile is a waterfront structures, and as the name suggests, that the sheet of small sizes are joined one by one, and you can have a particular wall to retain the backfill. The sheet pile normally it is made of steel, but it could be of precast concrete also. It is also wooden material, wood. So sheet pile, the materials are normally, these are the different types of materials that is being used, and it acts as a waterfront structure. You can join two sheets together by the connecting uh, element, and therefore you are going to have a sheet pile like this. So you can have the sheet pile, and this sheet pile, which is a thin element, can retain the backfill, and this is called the dredge line. And is used normally, these sheet piles are used as waterfront structures. Uh, for example, for dock facility, you can also have for berthing of ships, uh, etc. So many usage of sheet pile. In coastal area, you will find it, and also sometimes it is used as a, if you are going to have a uh, basement, or if you want to have the breast cut. So in breast cut also, breast sheet are used. So sheet piles have got many applications, but mostly it is used as a waterfront structures. So the water table is going to be like this, and these are going to be thinner elements, so the it can be driven directly into the ground, and the driving stresses are going to be so high that it can be even can be driven in a stiff soil also. Very hard soil, you can drive it because the driving stresses are going to be quite high, and therefore in soft soil and uh, if you want to have uh, a particular dredging, so the construction practice is like this. Construction of sheet pile. Let's say you have a zone like this, and you can drive the sheet pile here. There is the sheet pile, you have driven it, and then you can backfill it with the material. If you want to dredge it, you can dredge it also. So, and you can fill it. The backfill is going to be normally sandy soil. So, sandy soils are used as a backfill, and you can dredge it, and therefore this becomes the dredge line. So, you know, the application of seed piles are enormous, and mainly in coastal area for berthing of ships, and as a dock you can make use of it. So there are two types of sheet pile. One is called, you can just if it is a horizontal ground, you can directly drive it, and you can fill it with the backfill material here, and if you want to dredge it, you can dredge it and lower it. So this becomes the depth of embedment D. So this is the dredge line, and the sheet pile. And due to the backfill, there is going to be the lateral thrust over this. So it will just act as if it is a beam. So it is a cantilever beam. So it is called cantilever sheet pile. But if you put it here, let's say this is the ground, and you have driven it into the ground, and then you have backfilled it with sandy soil, and then if you put a anchor rod and then again backfill it, this type of sheet pile is called anchored bulkhead. So one is called cantilever. There is no anchor rod here, and if you are going to put the anchor rod, so this is the. So let us see the deflection pattern of the cantilever sheet pile. So it is a cantilever sheet pile. In cantilever sheet pile, you will find that this deflection is going to be like this. About some point O, it is going to deflect. This is the backfill. And there may be water table, and here is the dredge line. So rotation about O the deflected shape. So if you want to find out the depth of embedment in this case, D, we must draw the pressure distribution diagram. And as I told you, if the backfill is going to be sandy soil and below the dredge line, it could be sandy bed or it could be clayey bed. So how to draw the pressure distribution diagram? That's important. So lateral pressure distribution diagram. So, or horizontal pressure distribution diagram, you should be able to draw it. Let's say it is going to be sandy bed and the backfill is also going to be granular material, that is sand. Then how to draw the pressure distribution diagram? We know the deflected shape, and therefore if you try to draw the pressure distribution diagram, you will find that from the deflected shape itself, you can see that the zone above AO is going to be, the sheet pile is going to be going to deflect away from the backfill, and therefore this will be in active zone. So up to here, up to the dredge line, we may call it as zone 1. So it is going to be from here, the top to, or I can draw it here. Let's say so zone 1, and it is going to deflect here. So in this zone, below this up to O, let's say the top point is A, the bottommost point is, let us say, call it as B, and this the point of rotation O. So AB, I may call it as D, the dredge line. So between A and D, it is zone 1, and because it is going to deflect away from the backfill, it will be under active state or active condition. Now, below the dredge line between D and O, on the left hand side, you see, or on the front side, you see that this is going to deflect and it is going to compress the soil on this side. So this will be in passive state. So it will be in passive state. Whereas in this part, D2O, this will be on the right hand side of the sheet pile or on the back of the sheet pile, it will be in active state. So this becomes zone 2. So zone 2 is from D2O. Now, below this, you can see that this is going to deflect like this. So this is going to be in passive state. And this side, on the left hand side, it is going to be in active state. So sheet pile behavior is going to be complex, And if you draw the pressure distribution diagram, you can draw it easily. Here you will find it is going to be a active condition, and below this it is going to be like this. This is the pressure distribution diagram. So the pressure distribution diagram is a complex one. You can simplify it. So if you simplify the pressure distribution diagram, it will look like this. So pressure distribution diagram, if you draw it in a cantilever sheet pile, this is the dredge line, it will be the backfill, it is going to be active, this is the zone 1 in active condition. Here it is going to be a mixed condition in zone 2. It is active and this side it is passive. So it is going like this, and we can make it further like this, like this. So this becomes the lateral earth pressure distribution. So the lateral earth pressure distribution, I can draw it now like this. So cantilever sheet pile, the pressure distribution, let's take the sheet pile like this. So I have a cantilever sheet pile. Now this cantilever sheet pile is going to have the dredge line, the backfill top, and let's say the water table, right? So cantilever sheet pile. Now here in this, the top is point A, bottom we can call it as point B. So it will be here the unit weight is the bulk unit weight gamma, and below the water table it is going to be gamma prime. Therefore, and say the total height of the sheet pile above the dredge line is going to be h. Let's say this is h1 and this height is h2. Naturally, the total height is going to be h1 plus h2, and the pressure will be varying up to h1. The lateral pressure is going to be here. It is going to be P1 prime in terms of effective pressure, and then it could be drawn like this. Now it is like this. So this is P2 prime, and then it is going like this. This is the point O, and then it is going like this. So the pressure distribution diagram over the sheet pie can be drawn like this, and this is the pressure distribution diagram. This is B. So I may call this one as A, B, and I may call this point as C, this point as D. I may call this point as E, F, G. So the pressure distribution is like this. It's like this. If you extend it, I may call this as H. So here it is P1, P2 prime, right? And the from dredge line up to the bottom, I may call this this distance as D. D is the depth of embedment. So from the dredge line up to the bottom, this is going to be up to here. It is going to be depth of embedment. So D is depth of embedment below the dredge line up to the bottom most point of the sheet pile, right? And from bottommost point up to E, this distance is capital Y. And up to F, I may call it as Z. So the pressure distribution diagram has been well explained to you, and everything here. This distance from D to, they'll say D prime, D to E, this is going to be the distance A. So this is in active condition. This is completely, this is going to be in active condition. And the pressure distribution is like this. So I have already explained to you, this is in active state. Here, this is going to be passive. This side, it is going to be active. So active to, it goes to passive condition, and then it comes to here. This side, it is passive below O, and this side, it is active, right? So this kind of pressure distribution diagram, I hope you have understood it in totality. So how to find out this P1 prime, P2 prime? Let's say this is P, P, B1, and this side, it has been extended further, this line. So this is going to be P, P, B2. So let's calculate it. Very simple way we can calculate it. The depending upon the phi prime value, the angle of internal friction or angle of shearing resistance phi prime, you can say that this P1 prime equal to coefficient of active earth pressure into gamma into H1. That is the active earth pressure P1 prime. So the active earth pressure at C is going to be P1 prime, which is going to be K, where K is called coefficient of active earth pressure, and this is vertical pressure, gamma into H1 overburden multiplied by K will give you the lateral pressure or horizontal pressure. So PA prime, P1 prime is going to be K into gamma H prime. Now let's calculate P2 prime, which is at D. So at D, P2 prime is going to be again K into gamma H1 plus it is going to be now gamma prime multiplied by this distance H2. So P2 prime up to here it is K gamma into H1. It is above the water table, so we have taken gamma, and below the water table it's going to be this. And water pressure on the both side will cancel each other. Right. So P2 prime also you have calculated. Having known P2 prime, this P2 prime can be for remaining part, you see D prime to E, the distance is A. So A is the distance between D prime and E. So this is going to be both this side it is going to be active, this side it is going to be passive. So it will be Kp minus K, right? It will be Kp minus K. It is going to deflect like this. So if it is going to deflect like this side it is active, this side it is passive. Kp minus K into gamma prime into A. Therefore, A equal to P2 prime divided by K prime. Kp minus K is called K prime into gamma prime. So this you should remember it. Already from this P2 prime is known to you. K prime is difference between Kp minus K. Gamma prime is the material properties, again known to you. Therefore, A is known. So you have been able to calculate the value of A quite easily. Now it is going to deflect like this. So this side it is passive, this side it is active. So passive and active, and therefore now we can calculate further the value of Pp Uh, the Now for A, you can see what is this is going to be uh, K prime gamma prime into A. This is so for A. Uh, the slope, you can find it out for this. So the slope will be, slope of this can be easily found out, because you know vertical, you know horizontal. So for A, it is going to be horizontal K prime gamma prime. So you can say that for one vertical, the horizontal is going to be gamma prime K prime is going to be horizontal. So one vertical, there is the slope for this. So this is the slope. So for one, it will be one vertical, it is going to be gamma prime into K prime. Therefore, if this distance is y, this is being extended, no, up to the base. So for y vertical, the horizontal can be found out quite easily as gamma prime K prime into this distance y. So therefore, we can say PP B2, this one. This is the slope. So, which is at a distance y. So PP B2 will be K prime gamma prime into y. So PPB2 is very simple way you can calculate it. Now, at it is going to deflect like this. So once it is going to deflect about this point, and deflection is like this, you are going to compress the backfill on this side, and therefore you can find out the passive pressure, and that passive pressure could be found out here at E. The passive pressure E, or this is the point of rotation, so we can, E and O are same, so O or E, so we can say at this point it is PP O or PP E, you can write it. So how will you calculate this is again quite simple. So I can calculate, because it is going to deflect like this, the backfill is being compressed. So PPO will be Kp, passive coefficient of passive earth pressure, multiplied by gamma into H1, gamma into H1 plus gamma prime into H2 plus. Now it is going to deflect like this. So it is going to compress, but below this it is going to be in active condition. So plus Kp minus Ka below O or below E, it will be Kp minus Ka multiplied by gamma prime into this distance A. So you can calculate the value of PPO. So this is the passive earth pressure. So depending upon the deflected shape about E or about O, it is going to deflect, and therefore I am going to calculate Kp times gamma H1 plus Kp times gamma prime H2 plus this the active condition is going to be active and passive both in this zone, and therefore in below the dredge line up to A it is going to be Kp minus Ka gamma prime into A. So I hope you have understood what is this passive pressure at O or at E or PP at E. One and the same. The rotation is above O. Now this is known. This is known. Now what is left out is this. So let's calculate PPB1. Now this is going to deflect like this. So sheet pile is going to deflect like this, and therefore below O, this side it is going to compress it, this side it is going to be in active condition. So PPB1 can be calculated quite easily. Let us calculate PPB1. So will be Kp times gamma H1 because it's deflecting like this. So passive pressure on this side, it is under compression. So passive Kp times gamma H1 plus gamma prime H2 plus Kp minus Ka into gamma prime into D. So this is the depth of embedment, and it is for this it is going to be the mixed condition Kp minus Ka gamma prime D. So this is equal to Kp gamma H1 plus gamma H2 plus gamma H1 plus gamma prime H2 plus this can be written as K prime into gamma prime. Now D, the depth of embedment, can be written as A plus Y. A plus Y becomes the depth of embedment, and therefore if you further simplify it, this becomes Kp prime, Kp this plus, so this complete up to here plus K prime gamma prime A. Now PPO is Kp gamma H1 plus gamma prime H2 plus K prime gamma prime A plus. So up to here plus it will be K prime gamma prime into Y. Therefore, PPB1, this is going to be PP naught. So this is going to be PPO plus K prime gamma prime Y. So this becomes equal to PP at O, this one, plus K prime gamma prime into Y, right? So this expression, so in this pressure distribution diagram, we are in a position to calculate everything. So finally, PPB1 is PPO plus K prime gamma prime into Y. So that is the value of PPB1. PPB2 is already known. So PPB2 we have already calculated. So this is the fourth one. So everything this is known. This is known. P1 prime, P2 prime is known, A is known. In fact, everything is known. Therefore, we can apply the law of statics and find out the value from sigma h equal to 0. And we can also apply the moment about the base must be equal to 0. So for this cantilever sheet pile, apply law of statics. So applying law of statics, the algebraic sum of all the horizontal forces must be equal to 0. So let's say this is the active force from A to O, it is the active force, and its resultant is say capital PA, which is acting from O, this distance is say y bar. So now sigma h equal to 0 will be PA, that is the area of the active pressure distribution diagram, and that is called the value will be, or we can say like this is equal to area of sigma h equal to 0 means that is sigma h equal to 0, that is area of which one? We can say ACDE. So area of ACDE, which is this force PA. So this is going to be PA minus area of ACD minus the another area is going to be from here, it is going to be equal to EFHB. This area completely you deduct it. So you have deducted EFHB, this triangle. you are going to deduct it completely, plus this FHBG. So we can write it like this: BG. This area plus this area. So area of this, that is sigma h equal to 0. So this is equal to 0. Or we can say, or PA minus, what is the area of this EFHB? It will be half into base, the half into PPB2 multiplied by Y, this one. So that is the area of this plus this triangle. So whatever you have deducted, this part gets cancelled. So now you are adding it, and therefore this area will be half of PPB1 plus the base will be PPB2 multiplied by the apex distance. That becomes the area. So I am going to have this one must be equal to 0. So if you solve this, what is unknown? PA is known to me. So here, if I look to this equation, finally, from sigma h equal to 0, this is the fifth equation. So here, PA is known to me, PPB2 is known to me, Y is not known to me, Z is not known to me, this is known to me, this is known to me. So therefore, calculate Z in terms of Y. So if you calculate Z, this becomes equal to PPB2 into Y minus 2 times PA. Two times PA divided by PPB2 plus PPB1, or PPB1 plus PPB2. So we get this value of Z, which is unknown. We do not know what is this Z value in terms of Y from expression 6. So by applying the equilibrium equation, sigma h equal to 0, Z value in terms of Y you have calculated. Now you apply sigma m b equal to 0. So if you apply sigma mb equal to 0, let us see what we get. So the moment you apply this, the algebraic sum of the moment about the bottommost point of the sheet pile B equal to 0, then this PA into Y bar plus Y into plus Y minus this is the force, PA is over half PP B2 half PP B2 into Y into Y by 3. So it is going to be quite simple, into Y by 3. Then the third force is going to be this, half PP B1 plus PP B2 into Z by 3 must be equal to 0, sigma MB equal to 0. So this is here Y is not known, Z is not known, but from expression 1 Z is in terms of Y. So replace this Z in terms of Y, replace Z in 7 from 6. So in terms of Y, and therefore you will get equation, and therefore we get equation in terms of capital Y. So this whole equation 7, if you replace Z from here, the equation becomes in terms of Y. Must be equal to 0. And therefore, solving we get Y. So this Y is found out. Once Y is known, A is already known. Therefore, the depth of embedment we can find it out. Therefore, what is unknown? Therefore, depth of embedment D equal to Y plus A. Y you have found out from expression 7. A is already known to you, and therefore you know the depth of embedment. So friends, you have seen the complete solution of a cantilever sheet pile. So with this, I have completed the cantilever sheet pile, and I hope you have understood. I have tried to make it as simple as I can. And in the next video, I will take one example on cantilever sheet pile and solve for any real life problems. That will make your fundamental crystal clear. So thank you very much. Hope you have enjoyed.